I've started the recording.
Okay. Thanks for joining today. Today we welcome Dr. Sila Setinkaya, Cecil H. Green Professor of Engineering from SMU. She did her bachelor's and master's in industrial engineering from Turkey and did her PhD in management science from McMaster University. Her PhD thesis was primarily from inventory optimization, myopic policies for inventory control, and then she worked in Texas A&M for the last 15-20 years before she came to SMU as a full professor. She has received various awards and accolades from different institutions, and she is right now one of the youngest achiever in terms of many awards in terms of operations research, management science, especially on inventory control, stochastic optimization, and applications in healthcare analytics. On behalf of Inform's NCSU chapter, we welcome you, ma'am, for today's discussion. Today's topic, she is going to help us understand one of her PhD works with the students on the supplier side. If there is an transshipment or if there is a shipment consolidation, how the ordering policies can be derived out, and they used stochastic dynamic programming to find an optimal policy, and they proved again that this policy follows some kind of K-convexity proofs. So she will enlighten us today with the basics on the supplier side, especially on the inbound side, inventory consolidation, and what kind of math behind the process, so that we will get some understanding and that may be helpful for our research. Before I hand it over to Dr. Sila, I request Ajit to take a snapshot. May I request all the participants to open your cameras for a quick snapshot? Ajit?
Yeah, great. I will take this snapshot in 3, 2, 1, smile. Perfect. Thank you.
Thanks, Ajit. Ma'am?
Thank you, Srinivas-san. And it would be wonderful if you guys can keep your cameras on so that it's not just Srinivas-san and I here. I appreciate the introduction, and I also appreciate the invitation. It's a pleasure to present this group. Let me go ahead and share my screen and get this started. Can you all see my screen?
Yes.
Awesome. So the title of my talk today is The Impact of Outbound Temporal Shipment Consolidation on the Structure of Optimal Inventory Policies. This is a topic that has been of interest to me for a long time, and I will be giving you some background information about this research area in general and present some recent research results as well. This is joint work with one of my previous PhD students, Liking Zhang, and my colleague, Eylem Tekin, who is now at Rice University in Houston. Let me see. Okay. So the broad umbrella under which this research topic falls is supply chain coordination. And supply chain coordination has been one of my research areas for more than, I would say, 2 decades. And when I talk about supply chain coordination, I like to classify it into 3 areas, 3 interrelated areas. Horizontal coordination is coordination of decisions of interest within a given functional specialty of a firm. For example, if you're talking about coordination of inventory and transportation decisions, then both decisions fall under the functional specialty logistics of the firm. And then I say that we are interested in horizontal coordination. Vertical coordination is coordination of decisions that belong to different functional specialties within a firm. For example, if you're interested in coordination of inventory and pricing decisions, inventory decisions would fall under the logistics function, pricing decisions would fall under the marketing function, then I say we are interested in a vertical coordination problem. And then there's channel coordination, and channel coordination in my mind is always about the coordination of decisions of different entities within a firm. For example, decisions of retailers and suppliers can sometimes be coordinated under certain incentive mechanisms, and those practices are channel coordination practices. My focus today is on horizontal coordination. I will be specifically talking about coordination of inventory and transportation decisions. And horizontal coordination is a very important topic in the supply chain practice and research as well. And typically, horizontal coordination efforts are facilitated by vendor-managed inventory applications. This is particularly true for coordination of inventory and transportation decisions under a typical vendor-managed inventory program, or under a typical vendor-managed delivery contract. The vendor is empowered to make decisions regarding the timing and quantity of resupply at a downstream location, and this creates a framework for coordination of especially inbound inventory replenishment and outbound transportation decisions. These applications have been pioneered by Procter & Gamble back in the 90s, and then later Shell Chemical and many other big companies followed vendor-managed inventory practices, including General Motors and Intel. And I have personal experience collaborating with industry in the context of vendor-managed inventory applications, starting in the late 90s with Compaq and Hewlett-Packard, and lately and later with Applied Materials, and more recently with Dell and Air Liquide. I can assure you that the class of problems we are talking about when we refer to coordination of inventory and transportation decisions is very much of practical interest in industrial applications, especially in the age of internet deliveries and internet sales, where the vendor is responsible for the outbound transportation operation as well, in the context of deliveries to large retailers as well as to consumers. And if this is not enough reason to study integration of inventory and transportation decisions, here I have a slide showing you the economical impact of the cost savings associated with careful integration of inventory and transportation decisions. Inventory and transportation operations constitute a very large portion of the cost of the US business logistics system. The chart I have here goes back to 1999, the time period when the internet sales started booming. In the first decade of internet sales, the transportation and inventory costs together increased by about 40% nationally in the United States. And if you look at the numbers in 2019, 2020, 2021, the total cost is right now is at 1.6 trillion, another 15% growth in the last decade as well. So there is tremendous opportunity for cost savings if you consider the dollar values via careful coordination of inventory and transportation decisions, via integration of inventory and transportation decisions, via explicit consideration of the impact of transportation practices on inventory decisions. And indeed, this is the focus of my talk today. When I refer to integration of inventory and transportation decisions, I will be paying a particular emphasis on shipment consolidation practices and their impact on inventory decisions today. We classify shipment consolidation practices in academic literature into two. Sometimes we refer to geographical consolidation, and sometimes we refer to temporal consolidation. Geographical consolidation is self-explanatory term, and when we say temporal shipment consolidation, we refer to active intervention by management to combine many small shipments into a larger load with the aim of benefit from scale economies in transportation. And when we say temporal, we are basically saying that we are going to consolidate orders over time. There are several practical policies of interest when it comes to temporal shipment consolidation policies in practice. These are quantity-based policies, time-based policies, and hybrid policies, and I will define them shortly. But before that, let me reiterate the objective of the presentation today. The objective of the presentation is to introduce an integrated inventory replenishment and shipment consolidation model to you all, and characterizing the structural properties of the exact optimal joint policy in order to illustrate the interplay between inventory and shipment consolidation decisions. So what are quantity-based, time-based, and hybrid policies when it comes to shipment consolidation applications? When we refer to a quantity-based policy in the context of shipment consolidation, we refer to the case where the goal before we release a shipment is to accumulate a critical consolidated load. Say the goal is to consolidate Q units, or the goal is to consolidate, say, a full truckload, or the goal is to fill the 75% of the truck capacity. Whatever the target is, under a quantity-based policy, you have a quantity threshold. In most practical applications, demands arrive according to a stochastic process. So the time between demand arrivals are stochastic. And if you consider the stochastic nature of the demand under a quantity-based shipment consolidation policy, although you can guarantee a load that perhaps achieves scale economies, that perhaps achieves the minimum threshold, there is no way you can code a specific shipment release time, because the order arrival process, demand arrival process, is a stochastic process. So the main advantage of quantity-based policy is that you can achieve scale economies by choosing your quantity threshold carefully. However, you may or may not be able to achieve timely delivery expectations, because you may keep delaying the delivery of the load in order to realize the threshold. Under a time-based policy, you really do not have a quantity threshold, but you have a time threshold. Under a time-based policy, you commit to release a consolidated load every T time units. Demand arrive according to a stochastic process, typically. So under a time-based policy, you can code a specific delivery date. Say you can say, for example, you can code Mondays as your delivery date to all your customers, because you are releasing consolidated loads on a periodic basis, on a weekly basis. However, you cannot guarantee that within the time threshold, you are going to accumulate a sizable dispatch quantity. You don't know if you're going to fill 25% of your truck or 75% of your truck under a time-based policy. So the main advantage of a time-based policy is that you can quote the delivery time, you can achieve timely service, timely delivery expectations, but you are not sure if you will realize scale economies associated with shipping a larger or desirable load, whatever your load threshold is in your mind. Hybrid policies are designed to achieve or to balance, I should say, the advantages and disadvantages of quantity and time-based policies. Under a hybrid policies, you have both a quantity threshold and a shipment frequency. Your quantity threshold is Q. Your quantity threshold is Q. Your frequency is T. And the way the hybrid policy works is as follows. Under a hybrid policy, the goal is to consolidate a critical load of size Q and then release it by the time T. Okay? If, however, such a load does not accumulate within time period T, you release whatever the consolidated load is at that time. If the consolidated load of size Q accumulates before time T, then you release the order again. Okay, so you are, in a sense, balancing the timely delivery expectations of time-based policies with the scale economies benefit of quantity-based policies under a hybrid policy. All three types of policies are widely implemented in transportation industry. They are widely implemented in the context of vendor-managed inventory applications, vendor-managed delivery applications, and in the context of carriage shipping, common carriage shipping, shipping as well. Today's presentation, however, is going to focus on the exact shipment consolidation policy, which may not be one of these three policies, but it is important to know about these policies so that we can benchmark the performance of the exact policy against some of the existing and practical policies. So here is a representation of the problem of interest, just to illustrate the impact of shipment consolidation on optimal inventory policies. We are interested in optimizing the costs of the vendor in my figure here. The vendor receives inbound replenishments from a supplier and needs to decide on the replenishment quantities for those inbound replenishments. The vendor also responds to demands, orders from a market area. There is opportunity to implement shipment consolidation in delivering shipments to the market area, and the deliveries are subject to an explicit outbound shipment consolidation effort in the context of the problem formulation that I am going to present today. So the vendor has the liberty of holding smaller orders and releasing them as a combined shipment at a cost, and the vendor bears the costs associated with shipments to the market area, and hence the need to coordinate outbound transportation decisions with inbound inventory replenishment decisions. Inbound replenishments are received instantaneously. This is a simplifying assumption of the model and can be dispatched to the customer immediately. We can incorporate fixed lead times associated with inbound replenishments and outbound dispatch decisions once we know the exact optimal policy. And my focus today is demonstrating the exact optimal policy under the simplifying assumption that we have instantaneous deliveries both on the inbound side and the outbound side. Feel free to ask any questions if you have any questions. Let me pause here for a minute and see if you have some questions for me.
One quick question from my side, ma'am. Are you talking about this consolidated load primarily on a milk run basis where we get consolidations from different suppliers?
This is for the model that I'm going to present is on the is focusing on shipment consolidation on the outbound side. We are consolidating demands from, say, multiple retailers, or we are consolidating demands from the same from a single retailer. That might also be an option. The demands are stochastic over time, and they are observed over time, and you are sending one combined delivery. That's the assumption. So you know your target area, therefore you can think of this as a milk run. You are serving multiple demand points, or you are serving a single demand point with multiple stochastic demands that are consolidated in a given load.
Okay, so this is not exactly an inventory routing problem we are talking on the outbound shipment, right?
I'm not talking about an inventory routing problem. The assumption here is that we know the market area. We can characterize the demand of the market area. We are sending a consolidated shipment to the market area, but I am focused on the impact of the explicit shipment consolidation effort on the inventory policy, and it's not an inventory routing problem. It is closely related to inventory routing, but we don't have the routing optimization part embedded in it. We have the inventory and shipment consolidation policy optimization sides embedded in it.
Thanks.
Thank you. So 4 lines of previous literature are related to the model that I'm going to present today. The first line of literature is the large body of work on generalized inventory models under explicit transportation costs and considerations. The second line of related work is the traditional multi-echelon inventory models without consolidation, because the traditional multi-echelon inventory theory really does not consider consolidation efforts, simply assumes that all demands must be satisfied immediately. The third line of work that is related to my presentation today is pure consolidation policies. These are papers that only consider shipment consolidation efforts without coordination, without an attempt to coordinate consolidation decisions with inventory decisions or other logistical decisions or decisions of other functional entities within the firm. And the last line of work, and this is the most closely line of related work, is integrated inbound replenishment and outbound shipment consolidation models. There are some deterministic models and stochastic models within this line of work. And that is my next slide, since this is the most relevant line of literature to the presentation today. The deterministic demand case has been studied by multiple authors, including myself in past papers, but the goal of these papers is not to study structure of the optimal policy, but perhaps try to develop polynomial time algorithms to solve the problem efficiently. The stochastic demand case models, here I classify them into 2 categories: stochastic demand models with time-based consolidation, stochastic demand models with quantity-based consolidation. But neither classes of these consolidation policies, time-based, quantity-based, and also hybrid, they are not necessarily optimal. And when you are studying a stochastic demand model, either with time-based policy or quantity-based policy, you are restricting yourself to a class of policies. Therefore, you won't be able to characterize the exact optimal policy. And my presentation today is not going to make any one of these assumptions, and we are going to be interested in characterizing the inventory replenishment and shipment consolidation policy simultaneously. I have a few more results from the past literature, but in the interest of time, I am going to skip them, and I'm more than happy to share relevant papers and indeed a copy of the final paper that I am presenting today. If you would like to read it, I would be delighted to share it with you. And here's more about the problem characteristics with a little bit of notation. The vendor replenishes from the supplier at a replenishment cost. I call this the inbound replenishment cost and denoted by function W. The inbound replenishment cost includes a fixed cost and a linear cost. The vendor sends shipments. The vendor is responsible for the outbound dispatch scheduling problem and incurs an outbound transportation cost associated with this operation. I denote this cost function by capital C tilde. It includes a fixed cost associated with the dispatch, and it includes a linear cost that is charged against the shipment quantity. The vendor, of course, incurs an inventory holding cost on a per unit time basis. And because the vendor is implementing an explicit shipment consolidation policy, holding orders over time with the hope of consolidating a large load to be released to the market area, there is also a customer waiting cost denoted by W per unit time. All shipment consolidation policies, optimal, suboptimal, they are implemented at the expense of customer waiting. There is a little bit of a hold because you are trying to accumulate a larger dispatch quantity. Hence, customer waiting costs must be considered explicitly when there is an effort to consolidate shipments. As I mentioned, the classical multi-echelon inventory theory typically ignores these costs because the assumption there is that the transportation costs are covered by the customer, not by the vendor or the supplier. And the traditional applications have been such that this kind of assumption has been true, but in many of the contemporary applications, as you are aware, both industrial applications and also in the context of retail applications delivering to individual consumers, there are many cases where the vendor is responsible for the delivery, or there's a program for free delivery like Amazon Prime. So here is another slide with more details about my notation. I'll try to make this simple for you. So the key notation in terms of the decision variables are A and L. So the decisions for the vendor are the inbound replenishment quantity and the outbound dispatch quantity. The state variables of the dynamic program are X, on-hand inventory, and T, outbound load waiting to be dispatched. So at the beginning of each period, the assumption is that we observe our inventory level and we check our records to find out about the outbound load waiting to be dispatched. This is the load that has been consolidated so far by realized stochastic demands. We need to decide on the inbound replenishment quantity, and also we need to decide on the outbound dispatch quantity in each period. The optimal decisions are indicated by star, and naturally they depend on the state variables. The transition cost, which is also known as the single period cost for any action, the set of decision variables A and L with state xt, is given by the cost associated with an inbound replenishment if we choose to replenish, the cost associated with an outbound dispatch if we choose to dispatch, the cost associated with excess inventory we carry from period to period, I'm sorry, and the waiting cost. And clearly, I'm sorry, our dispatch quantity cannot exceed the available supply or the available quantity consolidated. This is a natural constraint on that decision variable. With this notation, we have the dynamic programming formulation, cost to go function, keeping with the traditional way of denoting things in dynamic programming. The cost to go function is denoted by capital B. Index N is for the period. We analyze the problem using the backward approach of stochastic dynamic programming. So the last period of the problem is period 0, and the first period of the problem is capital N in my notation here. The cost to go function then includes the single period cost that I have just introduced as a transition cost to, it is in blue on my slide here, and expected cost to go depending on the state variables. The terminal cost function is denoted by V0. This is the cost that is incurred at the end of the planning horizon. At the end of the planning horizon, the assumption is that you clear all outstanding orders. You dispatch the entire consolidated quantity, that is L is equal to T, and then you decide on the order quantity depending on your needs. This is a very complicated, this is an innocent looking, but a very complicated cost to go function, as I'm going to illustrate shortly. So in the tradition of stochastic dynamic programming solution approaches, let us first look at the last period of the problem, period 0. In the last period, you need to clear, you have an obligation to clear all of your orders. There's no more opportunity to consolidate. So the consolidation quantity is equal to the load that you have consolidated. There's really no decision to make at this point about the consolidated shipment quantity. The terminal cost then is based on minimizing the transition cost, the single period cost for the last period, based on the inbound replenishment quantity. And if you examine the terminal cost function, you can see that the right-hand side is increasing in the order quantity, and the optimal replenishment quantity for the last period of the problem is simply given by this expression, which means that you either place an order and obtain supply sufficient to clear the outbound load, which is T minus X, or you do not place an order. Your order quantity is 0. Plus notation is means that when T is larger than X, you order T minus X units, and when T is smaller than X, you do not order anything. This is, I guess, expected, and it is useful to analyze the problem further. Now, with this information, of course, we are interested in finding the solution for period N for all periods from 1 to capital N, considering the cost to go function. In order to solve the solution for to compute the solution for an arbitrary period N, here I introduce some additional notation, and I represent the right-hand side of the cost to go function, which needs to be minimized. This is the infimum operator equivalent to minimizing the cost function by notation small v. Okay, and with this decision, with this notation, I look at two cases and I say to myself, since this is a difficult problem to solve, let me try to decompose the problem in an arbitrary period in a meaningful way. What is the most meaningful decomposition for this problem? And then a simple idea arises. In a given arbitrary period, in terms of the shipment consolidation decision, you have two choices. You either dispatch or you do not dispatch. for an arbitrary period n. If you do not dispatch, then your dispatch quantity L is equal to 0. All you need to compute is the order quantity, and hence the cost to go function reduces to this new function that I'm defining UN1. This is the do not dispatch case. This is my notation for the do not dispatch case. Or you dispatch. If you dispatch, then you know for sure your dispatch quantity L is larger than 0, but it cannot be more than the available supply or the consolidated quantity, whichever is smaller. And then you still need to decide on the inbound replenishment quantity. So function U2 is representative of the cost to go function if I force myself to dispatch, if I say that I am going to dispatch. Then the overall cost function can be written in this form. Overall cost to go function can be written in this form. Cost to go for period n, depending on the state variables x and t, is either U1n. This is the case if I do not dispatch, or the minimum of U1n and U2n, depending on what I do in terms of the inventory replenishment decisions. Okay.
Ma'am, a quick question.
Yes, go ahead.
Okay, so here, whether it is do not dispatch or dispatch, I understand how the decomposition is done. But question here is, even still, if it is L equal to 0 or greater than 0, we are still yet to find the optimal value for A, right? So in that case,
of course, we are just trying to characterize the cost function a little bit, simplify the cost function a little bit from this form at the top to this form. I wish there was a further decomposition or simplification based on the inventory replenishment. There is none, but the dispatch and do not dispatch case leads to this modified formulation, which is greatly helpful to obtain more results by studying functions U1 and U2.
Yeah, that makes sense. Another question in the previous slides. So far, this entire formulation is based on a finite horizon formulation, right?
Yes.
Why we should not solve this in an infinite horizon problem?
Good question. In most inventory applications, and this is probably true for this application as well, although I didn't look at this problem, if you can characterize the structure of the optimal policy for a finite horizon problem, then the infinite horizon policy is very easy to prove, because typically the structure of the infinite horizon optimal policy is based on the structure of the finite horizon policy, as you can guess. But the finite horizon policy will have a more complicated structure because of the transient nature of the problem. You know, in the infinite horizon case, at some point you are in steady state, and some of your policy parameters will converge to steady state, and there is all this evidence from the literature in inventory control theory. If you know the structure of the finite horizon policy, the steady state policy structure is the limit of that policy as the time horizon goes to infinity. Okay. So you would need a different approach to analyze the infinite horizon problem. You wouldn't work with a total cost function. You would work with an average cost function. It is a technical problem of interest, but as far as I'm concerned, it's not the most immediate, most practical problem to consider, especially if you are successful with characterizing the finite horizon policy. I would argue that the finite horizon policy is more meaningful, more applicable. Very few problems in inventory control last forever. And we can also advocate for the infinite horizon policy as well, because infinite horizon policies are quite robust. Finite horizon policies converge to infinite horizon policies really quickly. You know, I have also done a lot of work in that domain, but here the focus is on the finite horizon policy. And I personally feel confident that the finite horizon policy, because it is characterizable here, although it's very complicated, provides the foundation for the infinite horizon policy.
Oh, thanks.
Mm-hmm. So this is the cost to go function. This is how it looks like. It's not convex in X or T. It's not monotonically increasing or decreasing in any dimension. So finding the optimal policy parameters is expected to be complicated. And here are a few analytical results. I'll try to not to bog you down with more technical details. This slide basically says that there is hope with characterizing the structure of the optimal policy if we can show that the cost to go function we have just showed belongs to a family V. And the family V is as described on this slide. We say that a function, an arbitrary function, capital V, happens to belong to family of functions script V if these properties are satisfied. These properties look very technical, but they each have a meaning, and they each have a meaning interpretation that is potentially applicable, that is realistic in the context of an inventory application. For example, assumption 4 basically implies that if there is no on-hand inventory at the beginning of the last period, the marginal value of the terminal cost with respect to the consolidated load exceeds the unit procurement cost, so that you do not have any motive, any opportunistic motive not to clear outstanding orders. Likewise, assumption 3 says that if the excess load is fixed, this is the load you need to release in excess of the available supply, the terminal cost is non-decreasing in the on-hand inventory level. That is, if you need to clear the outstanding orders, there is motivation to do so. So all of the assumptions have some kind of an interpretation, meaningful interpretation. Using the properties associated with class of functions script V, we can further analyze the problem at hand. We first analyze the case of the do not dispatch case, and lemma 1 basically reveals the optimal order quantity if we choose not to dispatch. And it basically says that if you're not going to dispatch, you should not be placing an order. And this is intuitive, based on abundant literature in production and inventory control, because if you're not going to release an order, there is really no reason for you to bring in additional inventory. Lemma 1 is true if the cost to go function of our problem belongs to family script V. Lemma 2 analyzes the dispatch case. It basically says that if the cost to go function belongs to family V, then we can characterize the optimal replenishment quantities based on the expression at the bottom of my slide. Okay, so at the bottom of the slide, of course, the replenishment quantity decisions are described or prescribed, I should say, along with the dispatch quantity decisions. And we have 3 cases. If the cost to go function belongs to family V, you either do not replenish and you clear all of the outstanding orders. You clear the entire consolidated quantity, and this is the case if you have sufficient supply. You don't need to order, but you can clear the entire consolidated load. The case 2 is you do not replenish, but you can only ship whatever is available in inventory as part of your consolidated load. This is the case, you do not have sufficient supply, but you still have a motivation to clear at least some of the consolidated load. And the case 3 is the case you replenish, you obtain supply, and then you clear the entire consolidated load. This is the case you do not have enough supply to clear the entire consolidated load, so you obtain some supply. This result basically says that in the context of this problem, a typical clearing policy is not optimal. That is, there is this case in the middle, okay, where you clear some of the outstanding load waiting to be released as a consolidated shipment using your supply, but you leave some excess load to be cleared in the future. Okay, this is actually a very interesting finding because all of the existing practical shipment consolidation policies that I have discussed, quantity policies, time-based policies, and hybrid policies, they are indeed clearing policies. And there is this notion in the logistics industry, transportation industry, is that clearing policies are indeed optimal, close to optimal, perhaps they are optimal in general. And this is a counterintuitive result going against that intuition. So this is an illustration of lemma 2 using a figure, that expression that I showed, the 3 pieces that I have here that demonstrate the optimal policy if you are going to dispatch. The result basically says that we have 3 regions of optimality depending on our state variables x and t. You are either in region 1, depending on your on-hand inventory and the consolidated load, and you do not replenish and dispatch the entire load because you can do that. You are in region 2, you do not replenish and you dispatch whatever you have. That is, you do not clear the entire consolidated load waiting to be shipped, or you replenish and dispatch the entire consolidated load. Now that we have the optimal policy for the do not dispatch case and the dispatch case, we can put these 2 cases together and present the entire optimal policy and prove theorem 1. Theorem 1 basically says that you have 5 cases if you comprehensively consider the fact that sometimes you dispatch and sometimes you do not dispatch. And the 5 cases indicate a threshold policy with a state-dependent threshold parameter, which I denote by H. Without giving you more hard time with my math and notation, I'm going to illustrate the solution using a graph. This is the complete optimal policy when you put all of the results together. You have 5 blocks, okay? In the first block, you do not replenish and do not dispatch. And this block is separated from the other blocks by this curve. And on this curve, this curve is dictated by your state-dependent threshold parameters. And blocks 2, 3, and 4 are the blocks that I have already described when I have explained to you the solution of the dispatch case. So block 1 is about do not dispatch. Blocks 2, 3, and 4 are about the dispatch case. And this kind of policy I call a zone state-dependent threshold policy. It's a new policy type within the class of all of the existing inventory control policies that we know. You may be familiar with some of them. from your coursework in production and inventory control. The simplest ones are base stock policies, SS policies, and QR policies. And here we have a zoned state-dependent threshold policy. The term zoned because we have two main zones, and then we divide the second zone into three subzones depending on the states X and T. Okay, and here I have some extra remarks regarding the optimal policy, explaining each zone. In the interest of time, I'm not gonna go over the details, but I'm gonna talk a little bit about the interpretation of the policy parameters before I wrap. The optimal policy is a zoned state-dependent threshold policy. In a given period, we have this threshold value H. This is the value of on-hand inventory that tells us if we should dispatch or not. And if we are dispatching, then we need to work in the zones 2, 3, and 4 of the optimal policy that I have just illustrated. The other parameters of the policy are delta. This is the maximum amount of excess inventory that you cannot afford to clear without placing an order if a shipment is dispatched. And then you have capital S. This is the optimal ending inventory replenishment inventory level if you indeed need a replenishment. You can think about the problem that I have just presented as a generalization of Scarf's seminal inventory model, for which the simpler SS policies are optimal. And if you ignore the outbound transportation costs and the outbound shipment consolidation efforts, the policy that I have just showed, the policy structure that I have just showed, reduces to a traditional SS policy. But indeed, in many applications, the outbound dispatch costs are significant. Therefore, traditional SS inventory policies may perform infinitely poorly, depending on the magnitude of the outbound costs. You know, the larger the outbound costs are, the worse the performance of the traditional policies would be. So just to wrap up, and I'm happy to share the paper, as I have mentioned, we introduced a new class of policies for the finite horizon version of the problem. The structure of the optimal policy provides a foundation for new computational approaches. I have not said anything about how to compute the optimal policy parameters. There's a lot of work that needs to be done in that domain. The new policy is also a foundation for investigating optimal policies under other generalized transportation cost functions. Here, we only considered a fixed cost associated with the dispatch and a linear cost. But for example, if the company is using a common carrier, the outbound shipment expenses may be subject to common carriage costs, may be subject to quantity discounts. You can think of all sorts of interesting cost structures on the outbound side, and the more general cost structures would lead to more complicated optimal policies. As I have mentioned, there's this common notion in practice that clearing policies are good, clearing policies are optimal or close to optimal. We have demonstrated with the structure of the optimal policy that clearing policies are not necessarily optimal. So the structure of the optimal policy provides a foundation for investigating the efficiency of clearing policy or benchmarking the performance of the optimal policy against other practical policies such as time-based, quantity-based, and hybrid policies. And I have already mentioned the relation of this paper to Scarf's seminal work with the explicit consideration of outbound transportation costs and shipment consolidation efforts. We are generalizing a very fundamental paper, perhaps one of the most influential papers in the stochastic operations research literature, and we owe the analytical results presented in this paper to the new class of functions we introduced, class V. The class of function, that class of functions generalize the class of K-convex functions, but that is a different seminar. So with that, I'm going to stop here, and I'm happy to answer any questions you might have.
Thank you, ma'am. Any questions from the audience? You can unmute and you can ask your question directly. Oh, in the meantime, I can ask a quick question. Ma'am, in this particular model, we assumed that the lead time from the supplier to the vendor is instantaneous, right? What happens if there is a lead time? Let's say a lead time equal to some T time periods or something. This will be a little complicated, I know, but how we need to bring that particular idea into place? Then we will have more blocks, right, in the final optimal policy?
Stochastic lead time, that is a brand new problem. And honestly, I don't know the answer to your question in the case of stochastic lead time, either on the inbound side or the outbound side. I would say there is still relatively little work on inventory problems with stochastic lead times, especially on the outbound side. There is very, very little. So we do not know the structure of the optimal policy. That is a big problem, interesting problem, a very challenging problem to investigate. The deterministic lead time case, I believe the case of deterministic lead time can be handled by the existing model. The structure, I claim that the structure of the optimal policy would not be impacted with a deterministic replenishment lead time, but you need to, rather than watching the on-hand inventory, you should be watching on-hand plus on order, and you should be making decisions. You should be triggering replenishment decisions based on on-hand plus on order quantity at the time of dispatch.
So this will definitely affect the flow of conservation, right? When it comes from the supplier to the vendor, we cannot exactly dispatch what we have at the vendor. So that, like in one of your blocks, we must deliver or ship only whatever material we have on hand, because it is still in order. It is yet to come. The optimal policy says.
Yes, that synchronization problem is a very challenging problem for stochastic lead times.
Okay. Thanks. And this SN, the variable you showed, the optimal inventory level, is it some kind of an order up to level? If we can put it
SN is your target inventory after you replenish and clear your orders. You can think of it as your some kind of a base stock level.
Base stock model. Okay, got it. It's an interesting idea. I've never seen these papers and this. Thanks for the presentation.
Thank you so much for inviting me.
Oh, sure, ma'am. It's our pleasure. Any last questions from any audience? Ma'am, if you don't mind, probably would you send the paper and this presentation for us? Maybe Ajit will stay in touch with you.
Absolutely. Thank you so much, Srinivasan. It has been a pleasure to meet you. And Ajit, thank you for the logistical arrangements. Thank you, everybody, for joining and bearing with me.
Thank you so much, Dr. Sheila. It is our honor and pleasure to have you with us in Informs NCSU chapter. I'm sure that we will have one more good occasion coming in the spring semester. We will have even more discussions on stochastic inventory theory and optimization. Thank you so
that
much,
would be
all the
great.
participants.
And hopefully there will be opportunities to meet in person, perhaps at an upcoming conference.
We look forward for that, ma'am. Thank you so much and have a great day.
Thank you. Take care.
Thanks a lot.